Okay, so today we'll go over some very important theorems from the textbook, some theorems that are very important in modular theory, and then do a couple exercises if we have time. So I will number all the propositions and theorems just like how they are in the textbook. If somebody wants, they can use the textbook as reference. So the first proposition is a very standard one. So let A be a ring and finally generated a module, then M is finally generated. Oh, I'm sorry. I'm sorry. No. I'm sorry. Is an A module. Sorry. It's an A module. Then, let's say M is finally generated if and only if M is a quotient of some A to the N. What I mean is direct sum. Okay, this proof is very easy. It's just group theory. So let M be generated by some finite collection of elements, and then consider A to the N is one copy of A for each of these elements, x1, x2, n. And so then, or I'll say that this is generated by the standard basis, let's say E1, E2. And then we can make a map from AN to M where each of the basis elements of A to the N maps to the basis element for M. So this is clearly surjective. So M is isomorphic to some quotient of AN. M is isomorphic to AN mod kernel. That is exactly what we're trying to prove. The other direction is, let's say, M is isomorphic to, let's say, A to the N mod B for some integer n greater than 0 and some module B inside A. Then we say that AN mod B is generated naturally by E1 mod B, E2 mod B, En mod B. This might not be a basis. We might have too many elements, but it's not wrong. So still generated by these. So as there's an isomorphism, that means M, so let's say A to the N mod B is finally generated. So M is finally generated. Okay, this is the easiest of the propositions we have today. Let's move on to the next one. So let A be a ring. M is a finally generated A module. And let's say I is an ideal of A. And let's say phi is an endomorphism. Of M such that phi of M is contained in IM. Then phi satisfies an equation of the form, let's say a relation. Satisfies the relation, I'll say something like phi to the n plus a1 phi to the n minus 1 plus a1 b plus A, N, I'm sorry. Where these AIs come from the ideal, not just the ring, but also the ideal I. And what I mean by phi to the n is composition.
Did you put the 0 for your relation?
Yes, sorry, thank you. Yes, thank you. And also, A1 times phi, I'm sorry, I'll say A1 times phi to the n is like, you do phi to the n minus 1, then multiply by an minus, I'm sorry, by 1. So this is actually a map. It's not it's not an element of the ring, it's a map. But this map is a 0 map. Okay, so I'm not going to prove this. The proposition's proof is purely linear algebra. So let's just skip it if that's okay. It's not that hard. It's just messy linear algebra. But we will go to corollary 2.5 that says, now we will start to actually try to prove Nakayama's lemma. So the first step is saying let M be a finally generated A module, let I be an ideal of IA such that IM equals M, that the statement of the proposition is there exists some X which is congruent to 1 mod I in A such that XM equals 0. So what I mean by this symbol means that X minus 1 is an element of the ideal. So let's actually prove this. It is extremely fast. So let phi be the identity map of the, I'm sorry, not the ring, but the module in proposition 2.4. Then what proposition 2.4 says that X is 1 plus, sorry, A1 times 1 to the n minus 1, all the way down to an minus 1 times 1 plus an. That's just the same as 1 plus a1 plus an minus 1 plus an. So this X, I'm sorry, this so this is the relation we had above. So that means that X minus 1 is in the ideal because all these AIs were in the ideal. Yeah, and that's correct. So, and then one last thing is that this X does in fact equal 0 in M. So X is the map, X is the element such that if you multiply anything by M, you get 0. That's exactly what proposition 2.4 says. Okay, so any questions here until we go to Nakayama's lemma?
Yeah, I'm good.
So actually, let me clarify. X is not the element of the ring. X is a map from M to M, where M is mapped to X times M. So this X map is an element of A, but I mean it is the term
Regarded as a map. Yep.
Yes, regarded as a multiplication by a constant map. Yes.
So that we can identify capital X with small x, right?
Yes, exactly.
Yeah.
This X does come from the the ring A, but it's the number you multiply every element in M by to get 0. So now let's move on actually stating and proving Nakayama's lemma. So Nakayama's lemma is sometimes confused by following, but for now let's prove I'm sorry, something happened. Let's prove actually Nakayama's lemma, and then we'll see that the corollary is more popular to use. It comes up more frequently. So the statement is that M be a finally generated a module. Say I is an ideal of A contained in the Jacobson radical. Of A. Then the statement is I times M equaling M implies M equals 0. So the Jacobson radical, if want to review, is the intersection of all the maximal ideals of the ring. We learned this in the first chapter. So how do we actually prove this? So let M, A, I be as above. So let all these three objects be from the hypothesis, and let's say let J be called the Jacobson radical. Okay, so that means that if I times M equals M, then because I is just an ideal contained in the Jacobson radical, and IM equals M, that means that JM equals M. So actually, there is from, how about I put a period? So from what we just learned, from proposition 2.5, there is an X in A, but X is congruent to 1 mod J, J is the Jacobson radical, such that X times M is 0. So this perfectly fits into the statement of the proposition 2.5, where in my case, the ideal started off as I, but it can also equal J. And so now, note that from X is congruent to 1 mod J, it implies that X minus 1 is equal to some, lowercase j in J. But what does that mean? That means that X is the same as 1 plus J. But if you have 1 plus an element of the Jacobson, that means that X is a unit. So if 0 equals X times M, then multiplying both sides by the inverse of X gets you 0 is the module M. Okay, so that's a proof of the Jacobson, of Nakayama's lemma. But usually, this corollary is a little bit more important than the statement of the Jacobson, statement of Nakayama's lemma. So any questions before we do the corollary?
Yeah, I'm good. Let's go ahead.
Okay, so let M be a finally generated A module. Let's say N is a submodule of M, and then let's say I is an ideal of A such that, I'm sorry. Let's say I is contained in the Jacobson, then the statement says if M is I times M plus N, then actually M is the same as N. So how do we prove this? So let all of these objects be defined like in the hypothesis. So if I let M be IM plus N, so let's apply Nakayama's lemma to not M or A, but apply to M mod N, which is an A module also. And then you note that I times M mod N is the same as I times IM plus N mod N, but that's the same thing as IM plus N mod N. Okay, and so that being said, if you apply Nakayama's lemma to this, it's very easy to see that Nakayama's lemma implies M mod N equals 0. So that means M equals N. Okay, so usually this corollary is used a lot more than the general statement of Nakayama's lemma. But of course, knowing the general statement is also very important. Okay, so let's review one more thing about tensor products, and then we can just start doing some questions. So this is given to you as an exercise in ATIA McDonald. I'll say let A and B be rings. Let's say M is an A module. Let's say N is, I'm sorry, let's say P is a B module. Say N is a comma B bimodule. What I'm trying to say is N is an A module. Let's say N is a B module. And for all X in A, we have X times, sorry, one sec. We have A times X times B is the same thing as A times X times B. Sorry, for all X in for all A in A, B in B, X in N, we have this compatibility. So then the statement says that we have that M tensor A N is naturally a B module. So even though there's this A here, it's actually a B module. How is that true? Because if you multiply any generating tensor by B, you get M tensor B times N. We have that N tensor P is naturally an A module because, oh, I'm sorry. A times n tensor P, A times n tensor P, and actually all of this is compatible by saying that this module is isomorphic to this module. So it's like this is an A module, this is a B module, and this is both, and this N seems to connect these two pieces together, the M and the P. So this looks very abstract and very confusing, but this theorem has helped me a lot in solving the questions for this textbook. Okay, I'm sorry. I'll do this. Any questions before we start doing exercises?
Yeah, I'm just wondering that, so as long as we consider two tensor products at the same time, so the intermediate stage, like n over here, so do we always assume that n must be satisfy the same assumption that you used?
So I think whenever a Tina McDonald says, A-B bimodule, then yes.
Yeah, I'm wondering that if there is an exception. So like the n just satisfy, for example, like A module or B module, but still we want to consider the tensor products several times at the maybe some reason, right? So
I think if certainly if it's only an A module, then this isomorphism is not even applicable. It's not, you can't even talk about it because it's not.
Yeah,
it'd just be strange.
Yeah, I totally agree. Yeah.
But yeah, I've only seen this question in this textbook because.
Got it.
Yeah. So I am done lecturing. So let's try to solve some questions. These are very technical because it deals with tensor products.
Yeah.
And you have to be very careful.
Yeah, it's so tedious, and yeah.
So this is one of the first times I used Nakayama's lemma. So let A be a local ring. Say M and N are finally generated. A modules prove that if M tensor N equals 0, then M is 0 or N is 0. So something very natural, but something that should be very natural, but it's very important we have finally generated. Very important we have finally generated. Why? Counterexample. Let M be Q over the integers, then M tensor M is 0, even though M is not 0. Why is that true? Because actually each of these terms I forgot why that's true. Yeah, I think this is true, but I forgot why it's true. Yeah, I know why. Because take any, I guess, A over B tensor C over D. This is going to equal A times D over B times D tensor C over D over the Z. And because this is a Z module, this is an integer, we can switch it around. So this is A over B times D, tensor product D times C over D, which is A over B times D, tensor C. But C is an integer. That's 0 in M. So the tensor product is 0, even though the module itself is not 0. So finally generated is important. So, sorry, I don't say counterexample, I say non-example. So why is this true?
So by the way, your counterexample also does not satisfy the local ring condition.
Yes, you're right. Yes. So I think there's at least a couple of things that are important to be careful of in this case. So yes, not counterexample, but non-example, but yes, very important. So finally generated might be necessary, and local ring might be necessary. So let's say A is a local ring with, let's say, maximal ideal, say I, and let's say A mod I is K, a field, right? So let's say A mod I is K, that's a field, and let's say that, I'm going to say that M sub K is K tensor product M, but that is A mod I tensor product M. We saw last week, 2 weeks ago, that this is isomorphic to M mod IM. So this is going to be very important in the future. So let's start with our question. Suppose that we have M and N, like in the hypothesis. Suppose the tensor product is 0. Then I can say that M tensor A tensor product with K is isomorphic to A N A K. And so remember, this is M tensor product. And so, like I said over here, so these are the same. This is just N mod I N. But this is equal to 0. Okay, so I'm going to need to use this later. So consider this module. So we made some theorems. We did a little bit of testing. Now let's actually try to prove what's going on. So consider this tensor product. So remember, and notice that in this case, this is K, this is K, this is K. So this is isomorphic to M tensor product A, K tensor product K, N tensor product A, K. Why is this equality, isomorphism true? That this is by exercise 2.15. That very strange question about the N is the AB bimodule. So this is isomorphic to M tensor A, K tensor K of N mod I N. Right, and so this is isomorphic to, if we switch backwards, we have, I'm sorry. So this is just M tensor A and mod IN, because you're tensor producting over the ring. It's just the ring, so you get the module back. Okay, but what was this equal to? This was the first thing I wrote over here. It's equal to 0. So actually, this is just 0. So what I actually said is M tensor A K or K. This is actually 0. But look at what's happening. These are K modules. This is again by exercise 2.15. But what is a K module? What's a module over a field? It's a vector space. And you're taking the tensor product over a field of 2 vector spaces. So M tensor K and tensor K equaling 0 implies one of these must be 0. Okay, and that means that by Nakayama's lemma, this is why we needed a local ring. That means that I is in fact J. This is why we needed a local ring. The maximal ideal is in fact the Jacobson radical. By Nakayama's lemma, either M is equal to 0 if this is true, or N is equal to 0 if this is true. Okay, so that's the conclusion. Okay, any questions?
So can you just remind me that how you use Nakayama lemma from the tensor product being 0 to M or N becomes 0?
Yes, so I want to show you that this is 0 implies, this is a good question. Okay, good question. Remember, M tensor AK is equal to M tensor A of, remember, K is just this. And then that is just M mod IM, right?
Now I can see, I got it.
Yeah, and so I is just a Jacobson radical, and then you can actually apply. Actually, it could just be the corollary of Nakayama's lemma. So the pieces are all there. I is not just an ideal, it's actually the Jacobson radical. And then I want to prove this is 0 implies M is 0. So in other words, if M is IM, that implies M is 0. In other words, if M is equal to Jacobson radical times M, then M equals 0. This is precisely statement of Nakayama's lemma. Yeah, good question. So yes, again, you have to be very careful. You're applying all of these theorems correctly. It's very hard. Okay. Would you like to move on?
Sure.
So let's try number 8. So number 8 says let A be a ring. then if, let's say, part A, if M and N are A modules, oh, I'm sorry. So they are flat A modules, then the tensor product is also flat. And if B, you know what, let's just do part A, because part B is very similar, but they use the language of an A algebra. It's the same proof, but we'll just do part A. How do you solve this? So remember, if I say this is a homomorphism of A modules, I want to be able to tensor this with the M tensor N and get, I'm sorry, I'll say is an injective. If there's an injective homomorphism, would tensoring it remain injective? I claim yes. So let's start. Let's actually just take the tensor product with M tensor N.
So at this point, R is just arbitrarily one, right?
Yes.
Okay.
Yes. So remember, what is this? What does this map do? It takes a basis element. I'll say R tensor X, and it moves it to phi of R tensor that same X. Okay, so remember that there is an isomorphism. I'm sorry, these are tensor products over A. So there's an isomorphism with this with these modules. So it's a natural isomorphism. It takes a generating element and it maps it like this. And of course, similarly, there is another isomorphism. It maps elements of this module this way. As tensor M tensor N to S tensor M tensor N. So it's almost like identity, but it's not, but it's very similar. Okay, so let's start completely over. We have a map, remember, like this here, with this injection, I'm sorry, with this isomorphism, R tensor A, M tensor A, N, and we also have this here. So S tensor A, M tensor N. So here is phi tensor 1 Mn. Here is that isomorphism mapping R tensor M tensor N to R tensor M tensor N, S tensor M tensor N to S tensor M tensor N. So is this actually, is this map here injective? Well, like we did last week, I don't care about this map. So long as I can give you a map here, which there is a commutative diagram, and if this map is injective, then I win, because it's just isomorphisms everywhere. Here, this map R tensor A, M tensor N goes to, phi of R tensor M tensor N. Okay, wait, what's going on? So actually, psi is just psi prime, psi prime with tensor product, the identity on N. You see that the N here is just identity. Okay, so that's fine. So that means that N is flat. So if psi prime is injective, then psi is injective. But look at what psi prime is. Psi prime is precisely phi tensor identity on R. We know phi is injective, and we know M is flat. So that means
identity on M instead of R.
Yes, thank you. Good one. Good catch. Yes, phi is injective and M is flat. So that means psi prime is injective, but that also means that psi is injective. Now, the final question is this map a commutative diagram? Well, certainly. It's so obvious it's certainly a commutative diagram. And so that means phi tensor identity on M tensor N is injective if and only if psi is injective, because it's a commutative diagram and everything on the sides are isomorphisms. So phi tensor 1 is injective if only if psi is injective, but it is. So that means phi tensor 1 is injective, and so phi is arbitrary. So that means M tensor N is flat. Okay, we're done. So we correctly answered 8A. So 8B is the language of algebra. We will do that right now. We'll maybe do that next week. So we solved the second question. So any questions?
Yeah. No questions. So I learned a lot.
Okay.
You want to stop here?
Much, do you want to do one more? Stop here?
Oh, it's totally up to you. If you feel it's reasonable to stop right here with the natural pace, then yeah, we can stop here.
How about one more question?
Sure, I'd love to.
It should be a natural application of Nakayama-sama again.
Yes, please.
So let's say let A be a ring. I an ideal contained in Jacobson radical, let's say J. So let M be an A module and a finally generated A module. And let's say U is a map, which is a homomorphism. Let's say that there's an induced map, which is a natural case. I'll say M mod IM maps to N mod IN is surjective, then the map we started with is surjective. How do we prove that? So let's say A, I, J, M, and N be as in the hypothesis of the question. So let's say that U maps M to N. So U of N is, I don't know what it is. I want to prove U mod N is equal to N. So to start with, I only know that U of N is a submodule of N. And so clearly, we have N is the same as IN plus.
Also about the notation. So U of N means the image of right? Got it.
Yes.
Got it.
Yes. Yes. So N is actually equal to U of N plus a little bit of a factor, which is not in the image, because given N in N, we have N plus IN is an element of here. Understand? So there is an M and M such that, let's say, U twiddle of M plus IM equals N plus IN. I'm sorry. Is U of M plus IM is N plus IN, because it's surjective, right? And so that means U of M minus N is actually in N. But that means that this is in the image of U, which is U of N, and this is IN. So N is equal to U of M plus some X. X is in IN. So we do have that N equals U of M, I'm sorry, plus IN. Oh, I see what you mean. I'm sorry. Silly mistake.
Yeah.
Yes.
I was confused. Yeah.
This is my mistake. Yes. So this is true. Okay. It looks like I have to use Nakayama's lemma. So and so clearly, actually, this is not true. I didn't actually prove this. I just proved this. And so how do you prove this, the other side? So clearly, U of M and IN are submodules of N. And so we have an equality. So actually, N equals U of M plus IN. Okay, but like I said before, let me just see something. So remember, I is contained in the Jacobson radical, and so that means that N equals U of M plus IN. It implies by Nakayama's lemma that n mod in equals 0. Actually, no, sorry. Sorry, one second. One second. So this is precisely if you apply corollary 2.7, this is precisely what it means that n equals u of m plus in implies n equals u of m. That's precisely what it means. And so we are done. So we prove that this is a surjection. Thus, u is surjective, which is what we were trying to prove. So this statement here is precisely the statement of corollary 2.7.
So this argument seems not applicable for the injective case. I do not know the counterexample.
I don't think so. I don't either. I think because you're modding something out, when you mod something out, you lose a lot of information. So you can't necessarily
Yeah, there might be counterexample. Yeah, I think so. Got it. Yeah, thanks for this exercise as well. So do you want to stop here?
Yes.
Okay, then I'll stop.